Good evening. Welcome to week 4 of the Nuclear Masterclass, and this week is going to be medical physics. My name is Kate Revilius. I'm a science journalist based here in York, and I'm going to be chairing tonight's event. Before we get started, just a few technical points about the webinar. If you're watching live, you can ask questions at any time using the Q&A button, and I encourage you to do so. There are subtitles available for today's webinar, and you can switch these on or off using the CC Live transcript button on your screen. If you get any technical issues during the webinar, you can always rejoin again using your original link. And please remember that this webinar is being recorded, so will be available to you during the coming weeks alongside other material on the website which you already have access to. So, this evening's event is, like previous weeks, going to take the form of two 15-minute presentations followed by questions from you, the audience. A reminder that you can submit questions through the Q&A button at the bottom of your screen at any time, and I will put them to the speakers at the end of their talk. So please do keep your questions flowing, and I'll do my best to pose them to the speakers. So, without further ado, let's introduce our first speaker. So, our first speaker is Thomas Kokolius. He is a French-American nuclear physicist based at KU Leuven in Belgium. And after studying in Canada, he obtained his PhD in fundamental nuclear physics at KU Leuven, and he studied the shape of exotic nuclei. He was a research fellow at CERN and an Ernest Rutherford Fellow at Manchester before he started becoming a lecturer at KU Leuven in 2015, where he's now a senior lecturer. Thomas, welcome.
Thank you for the nice introduction, Kate, and thank you everybody for being here today. So, nuclear weapons against cancer. What? Let's have a look into that. First, what makes a nuclear weapon? What are the different parts and ingredients in that? You first have a missile that carries a payload. Your payload is nuclear in essence, and you have a guiding system. You don't want to drop that anywhere. You want it to reach exactly where it needs to be. So, can we use that same concept against cancer? And the answer is absolutely. We call that a radiopharmaceutical. It is a molecule that we can engineer so that it targets specifically cancer cells to go and destroy them. Instead of a missile, you use a chemical construction, a chemical molecule. We call that a chelator that will carry the payload. You load this payload with something radioactive, typically one isotope that you're interested in that has the right properties that will target then the cancer cells. And finally, you need a guiding system. And such a guiding system can be, as we presented here, an antibody. Now, what more precisely can we do as guiding system? How can we make sure that the radioactivity goes to the right place in the body? You've heard already in this masterclass about the danger of radioactivity. Why would you inject that into a human being, especially one who's sick already to begin with? Well, there are actually some tricks we can play around that. One of them is that some specific elements get taken up by the body at specific places. The iodine, for example, gets taken up in the thyroid. And if you have a cancer of the thyroid that gets metastasized and that the cells just start traveling all over your body, iodine will travel where those cells are and will be specifically taken up by them. Now, if you take a radioactive one, it will work perfectly for this. And this is not just a random example. This is one that will come back in the next presentation by Dr. Sinclair, who will introduce to you how this is actually done in practice. And for information, this treatment has treated up to today 10 times more patients and saved 10 times more lives than all the nuclear incidents put together through the history of time. Isn't that impressive? The second possibility is to take a molecule that's normally used in the body, like a sugar molecule, and replace one of its elements by a radioactive one. An example of that is the sugar equivalent called FDG, where a OH complex is replaced by a radioactive fluorine. This allows to map where sugar is taken up. For example, in cancer cells that are very active and eating a lot of sugar, or to map brain activities. Say you want to see what part of the brain flashes when you're playing the piano or solving a math exam. And the final way that resembles what I was showing before are the very much engineered molecules where we do all this linking and building up. For those, you are basically targeting receptors that are at the surface of cells. Some cells, especially cancer cells, will change the expression that they have on their outside. And if you find one that's specific to the cancer you want to target, but is not expressed anywhere else in the body, then you know it will go there and only there. And that can be done, for example, with small peptides, with hormones, or with complex molecules such as antibodies. Very good. Now we have the guiding system. We understand also more or less what the chelator does. But the other aspect is, how do we get to the right isotope? And there you have to remember one thing. Radioisotopes have a half-life. They decay. If they're too short-lived, they will not get there in time. If they're too long-lived, you might actually release them before it does its action. So you need to make sure to map this half-life to however long that molecule is staying in the body. We call that the biodistribution. Okay, half-life is one point, but what are the other? You have to look at the properties of those radioisotopes. And those properties are here in the top right corner, where, if you remember, charged particles like alpha and beta particles will tend to travel very short distances and deposit their energy very quickly. Whereas gamma radiation is highly penetrative and will go very deep. Or if coming from the inside, will be able to come out. And that's why, for imaging purpose, to look at what's happening, you need to have something that will emit a gamma ray. And we'll hear more about that in Dr. Sinclair's presentation. Then the other aspect is for treatment. If you want to selectively destroy cancer cells, for example, for that, you need to deposit all that energy. And especially you want to damage the DNA, because breaking the DNA is what will cause the cell death. If you compare now a beta to an alpha particle, it's a bit like comparing how sometimes a truck that's not under control anymore needs to be stopped on the highway by ramming into those big barrels of water that you might have seen driving around. And if you're a big truck, you will like bump into those barrels and lose your energy quickly. That's what an alpha particle does. It's big, it's heavy, and it's going to ram all its energy into a very localized position. But if you compare to that, a beta particle is more like a bicycle. And if you come to that with your bicycle, you might bump into one or the other barrel, but somehow find your way through them. And this is what the beta particle does. All in all, it means we really want to have alpha particles. But you see, it's not that easy. And again, I remind you, have the right half-life. So now, if they're all good and nice, those techniques, why isn't that more developed? Why haven't you heard of all of that earlier? Well, it's because it's rather complicated as well. And it brings me to the medical radioisotope conundrum. Here you see the nuclear landscape with all the over 3,000 radioisotopes, but only a handful of those are actually used in medical practice. In its 2014 survey, the Nuclear Physics European Collaboration Consortium reported that out of all the imaging, not therapy, but imaging isotopes, 80% of the time, it was technetium-99m that was used. And that's why actually Dr. Sinclair will give us some information about that in her presentation, because it's so prominent. But it cannot be that one size fits all is the answer. Notice here as well, the iodine has quite a substantial component, but nonetheless, it's too few. And why is that? It's because they're simply not available on the market. They're not available for medical doctors to pick up. They're not going to do research with it. If they don't do research with it, there will be no demand. There is no demand, there is no production. And you see, it's a vicious status quo that you can never get out of. So we need to find an alternative supply chain to support this. And this is what I, as a research nuclear physicist, try to do to provide that so that they can go further. How do you choose the right payload, though? That's a very interesting question. So let's look at this specific corner of the nuclear landscape, where we know we have a lot of alpha emitters. First off, you have to select those that have a substantial branching ratio, so only the yellow ones. Then you go to limit yourself to half-lives that are reasonable to work with, at least a few hours, but at most a few days. Let's say 2 weeks is the hard limit you place. And you see that it's already a substantial limit. Then you have to make sure you can work with them and they have the right chemistry, but okay, let's leave that to other researchers. But also that you can produce them. And then you realize all those super heavy elements in there are definitely not appropriate. So you are left with only 7 isotopes out of this entire region. Actually, even 3 of those only are actually used in research today. And if you go through the rest of the nuclear landscape, only 3 more are added. That's, you can count them on your fingers. It's very few. And the other point is only 1 radium-223 is currently used for only 1 treatment. So there is a long way to go. Let me bring your attention now to a specific choice of isotope. That's the terbium-149 and its other isotopes 150, 255, and 161. The interest in this group of isotopes is that they present different properties. You can see here how this one is very good with alpha emissions, perfect for alpha therapy, while terbium-161 has beta emission for beta therapy, and the other 2 have the right properties to be used for imaging. So if you find the right molecule, if you engineer the right delivery mechanism, you can selectively swap between those different isotopes, depending on what you want to do, image or treat. And then, very important, you have a lot of different half-lives from a few hours for the 2 lightest up to almost a week for the heaviest, which allows you to select the right one for the right biodistribution. How do we produce those isotopes? Well, 161 is readily available from nuclear reactors by doing neutron capture on gadolinium 160 to produce 161 and letting it decay. After that, you can simply perform radiochemistry to extract the terbium. The other 3 are a lot more difficult because you have to start either from the lighter stable gadolinium isotopes, but then you see how many neutrons you need to boil off to get to that very lightest terbium isotope of interest. And that just is a very dirty process. Also, you have all the different gadolinium, which makes it a lot more complex. An alternative is to start from europium and bombard it with alpha particles, because at least you have only 1 europium to begin with. But it's also a lot of neutrons that need to be evaporated. It's rather difficult. This is nonetheless being investigated, for example, with the Cyclotron Center of Birmingham. Finally, the way that we use at CERN to produce those is to use very high energetic protons, bombard some heavy material like tantalum, and then produce this entire region from which we hope to be able to extract the terbium. How do you do that, you may ask? And this is where my research comes in, the isotope separation online technique. The same technique that is used to produce radioactive beam for fundamental research can also be used to produce radioisotope for medical applications. And we do that, for example, at the ISOLDE, the ISOL device facility at CERN. This facility works as follows. We first bombard a thick target, maybe 20 centimeter in length, with high energy protons. Those induce a lot of different nuclear reactions that will produce over 1,000 different isotopes of 70 to 80 different elements. It's quite a lot. Those are then extracted from that material by keeping it at very high temperature, above 2000 degrees. We then bring them to an ion source where they are transformed to 1+ ions and then subsequently accelerated to an energy of 30 to 60 kiloelectron volts. This monoenergetic beam is shaped and sent through the homogeneous magnetic field from a dipole magnet that will allow to separate it according to the mass over charge ratio. Having only a +1 charge, it makes it a mass separator. And at the end, we collect the sample at the end of this beam pipe. So the first step is the production, where we send the proton beam onto this heavy target, And you see here the different types of target materials we may use. Those here are rolled tantalum foils that I was mentioning for the production of the terbium isotopes. But we can also use compressed powders, like here with boron nitride, or up there with titanium carbide. Once the proton hits this little grain here of microscopic size, you first have to let the material diffuse out of it, which is a rather slow process. Then it diffuses through pores in the material, through the chamber of that contains the target material, where it finally reaches the ion source. And all of those have different efficiencies that, of course, cost you a lot. So there's a lot of research ongoing into improving those efficiencies. The second step is the acceleration, and it works the same way as letting a ball roll from up a hill. You start on a high potential energy and you convert it into kinetic energy by letting it roll down. Except instead of doing that with gravity on height, we do it by putting this entire unit I was talking about before with the target and the ion source on a high voltage, which allows us to release the ions in specific energy. The third step is the mass separation, which we perform through a magnetic field. The kinetic energy that we have is related as such to the velocity, but also to the mass, which means the velocity itself at which the beam travels will be proportional to the mass. If you look now at the force that is being exerted within this dipole magnet, it will be proportional to that velocity, so that this entire process at the end and the path that will be followed will be a function of the mass. Intuitively, the force will be always the same, but if you're lighter, you will be pulled more, and if you're heavier, it will be harder to pull you. Altogether, it means we can select a single mass. The facility that we employ to perform this for medical isotope collection is actually built on the back of Isolde and is called Medisys. It is similar, but a different entity. It started only in 2013, while Isolde itself is 60 years old. But since 2018, it's been regularly producing radioisotopes and has allowed us to deliver already more than terabecquerel. The activities we do there is based on collaboration board, where we select the projects and get them approved. Note here that the UK is a member of Medisys, especially through the National Physical Laboratory in Teddington. Now, let me give you a small 1-minute overview of a bigger project at the European scale. Within this European consortium, we also have educational material at our disposal and at your disposal. So please visit prisma.eu for more information, and don't hesitate to recommend that to your instructors as well, because they might find material there that can be relevant for your classes. And with that, I bring my presentation to a conclusion, because that's only the beginning. Producing those isotopes is a challenge, but then it's the first step in a long chain of research that will bring it to a radiopharmaceutical. And we will now hear from, in the next presentation, how this actually is used in the clinic. Thank you for your attention.
Thank you, Thomas. That's absolutely fascinating and really heartening to hear how fast things are changing and how much is happening. I wondered if you can tell us a little bit about what kind of possibilities or advantages you think might come out of developing these other isotopes. What can they bring that we haven't got already?
I think the terbium is a very good example of theranostics, which is how you can fuse therapy and diagnostics together. By having this opportunity to swap between molecular imaging and therapy, you can actually verify first that the treatment is going to work and is going to go exactly where you want to that patient. By doing it quantitatively as well, you can make sure that you tune the therapy to the exact needs of the patient. And instead of shooting in the dark and saying, maybe you can try this or we can try that, and hoping you do more good than damage, you can actually tailor to really tailor the treatment to the patient and arrive at personalized medicine. And this is what we are thriving for.
That's amazing to think of. A question that's just come in from the audience. How are the samples stored and made into those specific radiopharmaceuticals?
Yes, it is a multi-step process. So when we do the collections, we actually collect those on the surface of metal foils. We use gold because it's very resistant, it's not very reactive, and we put a small layer of aluminium on top. After we've collected into that layer of aluminium, we dissolve it with acid so that it can be in an aqueous solution. From there, we can perform various chemistry stages to really extract only the isotopes of interest. And then we can perform further chemical reactions to turn it into the medical isotopes, the radiopharmaceutical of interest, that can then be injected into the clinic. So from physics to radiochemistry to radiopharmacy to back at the medical physicist, it's a whole chain that allows that. Naturally, it is radioactive, so you have to do all of those, taking care of shielding and protection and transport. I mean, if you want to transport a small vial, you need a big lead bucket that is placed itself in a big container that is transported on a big truck. So that makes it a logistic challenge. That is one of the research aspects we keep investigating.
Okay, I'm going to leave it there for the moment and introduce our second speaker for the evening. So, Laura Sinclair is a medical physicist who currently works in St Thomas's Hospital in Dublin, Ireland, and she completed her PhD in the nuclear team here in York. Welcome, Laura.
Thank you so much for having me this evening. I'm very excited to be here. So we've had Thomas's wonderful talk that described about discovering medical isotopes, bringing them into research. And I'm going to be talking about the clinical application. So I am a senior medical physicist at St James's Hospital in Dublin, and I work in a hospital in a clinical setting, predominantly in nuclear medicine. So I am often asked, mostly by my mother, what is a medical physicist and what do you do? So I'm going to give a brief overview of that today, and I'm going to talk about nuclear medicine, radiopharmaceuticals, how we get them into the pharmacy, into the hospital, and then break it down into nuclear medicine imaging, non-imaging, and radionuclide therapies. And then I'm just going to give you a brief overview of my working week, of my routine tasks, and all the things that come with it. So, what is a medical physicist? There are many different areas that medical physicists work in within the hospital, and pretty much every imaging application will have a physicist behind it working there somehow. So we can break this down into diagnostic imaging using CT, fluoroscopy, mammography. So these all use X-rays. And then we have ultrasound, which uses sound. And we have magnetic resonance imaging, the big MRI magnets that is very, very clever. It flips the hydrogen atoms within your body using the giant magnet and uses radio waves to get an image back. And then we have UV phototherapy, we have nuclear medicine, PETs, lasers, and then there's another aspect of being a medical physicist which might be involved in radiation therapy, so using proton beams, conventional X-rays, brachytherapy, which means contact therapy. So These are all the areas that physicists can work in behind the scenes and within the hospital, and of course in research. So, what is nuclear medicine? This involves the application of radioactive pharmaceuticals for diagnostics and therapy applications. Nuclear medicine imaging provides functional information, and we can also use it in other areas of diagnostics, which I'll be describing a little bit later. And then finally, we've got radionuclide therapy that uses alpha, beta, and gamma radiation to treat many different medical conditions. So, as Thomas has described, one of the big areas is in cancer, but we can also use radioactive iodine to treat benign disease as well, and bone marrow disease. So, there are many different applications. So, when we talk about radiopharmaceuticals, as Thomas has described as well, we've got two things to think about: the pharmaceutical and the radionuclide that is going to be attached to. So the ideal radiopharmaceutical, so for the pharmaceutical component of it, we want it just to localize in the area of interest. We don't want to give a radiation dose to other parts of the body if we can help it. And ideally, we want it to be simple to prepare because we have a basic radiopharmacy, so we might just need to shake it or heat it. And the radionuclide, we want it to have a long enough half-life that we can do the imaging and that they can be localization, but short enough that we're not giving a big radiation dose to the patient. We only want it to emit gamma or X-rays for imaging. We don't want any alpha or beta particles. We don't want to be given radiation dose and damaged cells. We don't want any charged particle emissions. We want it to be chemically suitable, so we want to be able to add it to a pharmaceutical so it's stable, and we want it to be readily available, and ideally a photon energy between 100 and 200 keV, and that's for a special piece of equipment. So we have the molybdenum and technetium generator, and here is a picture of a cutout of one, so you don't actually get to see the inside of these very often. So molybdenum has a half-life, it's molybdenum 99, I should say, has a half-life of 66 hours, which is a lot longer than technetium 99M, which has a half-life of 6 hours. So obviously we wouldn't be able to transport technetium as much as we need it. So we might prepare a kit for 8 a.m., for 9 a.m. So we need to be able to have this on site. So we have a molybdenum technetium generator. And then what we do is called eluting or milking the generator. So we can add a vial which pulls the saline through the generator and washes off the petechnetate, the technetium, into this vial, which we then can use to prepare kits for the patients. We use technetium for 80% of our procedures within the hospital, within the nuclear medicine department. So it is the workhorse of the nuclear medicine department. And we are able to transport these generators large distances. So currently, a lot of these generators come from mainland Europe. A lot of them come from the Netherlands. So they are transported quite large distances on a weekly basis. So when we talk about nuclear medicine imaging, instead of like the conventional x-rays where the x-rays are being transmitted through the patient to form an image, the patient becomes the source of radiation. So the radiopharmaceutical is administered to the patient, and we can either do this through intravenous injections with capsules, and we can even get the patients to inhale. So it all depends on what the clinical question is and how we're going to administer the radiopharmaceutical. So when the radiopharmaceutical has been localized, the radiopharmaceutical is emitting gamma rays, which then can be detected by a gamma camera or different probes, but in this case, we're talking about the imaging. So the gamma rays are emitted in all different directions. So we have to be able to create an image from this. So we can use the gamma camera, and we've got different components. So we're changing this gamma ray into an electrical signal, which is going to form our image. So first of all, the gamma camera, we have a gantry, and most of them have at least 2 detectors. Some have 1, some have 3, depending on the design. And we have a patient bed, so most of the scans are performed with the patient lying down, and a dedicated computer. So as you can see in the diagram for the detector, we have the patient, and we have the photon traveling through a collimator. So the idea is that the photons traveling in a straight line, the gamma rays photon, traveling in a straight line will be detected, and anything that is scattered will not go through to our signals. So this is to try and reduce the scattered radiation through the patient. And so once it's gone through the collimator, it is then detected in the crystal, and we'll then go to the photomultiplier tube, so it creates many electrons, and then we can put it through the preamplifier, and then we can create an image using different imaging reconstruction techniques. So we'll get this visualization of what's happening within the body. Also, we can use nuclear medicine in a non-imaging way as well. So a couple of examples I have is sentinel node localization. So for patients who have melanoma or certain types of cancer, we can inject them with a small amount of technetium-99m paired with a radiopharmaceutical, paired with a pharmaceutical. And in theory, it's going to move to the sentinel node, and the surgeon can then remove this node so they can use the probe to detect where the radiopharmaceutical has localized to. And the probe is just a little crystal that is used and will make a noise and flash up numbers when it detects the radiation. And then we've mentioned radionuclide therapies briefly, so did Thomas. And so when we give the patients an iodine capsule, we might give them a test capsule the day before just to see how much of the thyroid is remaining. So we give them a small amount of activity and give it 24 hours to localize. Most of it's going to be flushed through the kidneys, but a small amount's going to be within the thyroid itself. And then we can take a measurement with that. So it's another probe, another non-imaging technique. And then we have radionuclide therapies. So this is a big part that physicists have a hand in. And I've given you an example of an inpatient radionuclide therapy room. So this is used for our iodine 131 patients. So patients who have thyroid disease. So most of these patients would have had their thyroid removed before, and there are still cells remaining in the body. There might be metastases where it's moved. So this is when the cancer's moved to different parts of the body. And we're trying to do a targeted therapy. So the thyroid cells are avid for iodine. This means they will take them up. It's the only organ in the body that will take it up. The rest of it will be passing through the body. And so this comes with its unique challenges because we give them quite a high dose. We give them an activity in the gigabecquerel region, whereas for imaging, we give them in the kilobecquerel, megabecquerel region. So we have to consider radiation protection measures for the staff, for people in other parts of the hospital. So this room, it might look like a regular room. It's actually lead lined. And this is just to prevent some of the gamma rays from leaving the room and irradiating people nearby. It's got quite thick concrete as well. And the patient has a private bathroom. And this is just because most of the iodine is actually going to flush through the system, go through the kidneys, and go down the drains. So we want to make sure that any spills that might arise from there are contained within this bathroom, and we are discharging not to other parts of the hospital. We have a hatch in the room as well, and this is because our auxiliary staff will come and feed the patients, but we don't want them to interact and get a radiation dose for those first couple of days. So we can pass the food through the hatch just to minimize contact with people. We also cover the floors as well in either bench coat or something known as Pac-X, and this is just to stop radiation spreading through the room. And after the patients leave, we can lift it up and put it into a designated waste bin. And the bins are also lead lined as well, because a lot of the stuff that the patient will be touching becomes contaminated. So we put special bins in the room, and then we can take this waste and put it in a radioactive storeroom and wait until it decays. And we also have minimal items of furnishings in the room, just because everything the patient touches will just be slightly contaminated. So we just want to minimize the amount of radiation and contamination within that room. So a physicist will help design this room and try and have the practicalities of being within a hospital. Sometimes some hospitals might have to return this room after it's been used for other patient use, so it has to be easily cleaned. Other hospitals will have this room every single day of the year. So it really depends on the hospital and the challenges that will come within that. So I thought it'd be quite interesting just to give you a brief overview of what the nuclear medicine timetable may look like. So for myself, I'm in the radiopharmacy 3 days a week on a Monday, Thursday, and Friday. And on a Monday, this is when we get our new generator. So there's a few tests that we have to do. So we've got a pharmacy preparation aspect and a radiation protection aspect as well. So when we install the generator, we'll perform special tests. Some of it is to make sure that the aluminium column holds the generator hasn't broken in transit. If it's dropped, some aluminium could come off, and we don't want to inject that into the patient. So we have a simple test for that. And then the other part is to make sure that the molybdenum hasn't come off the column as well, as the molybdenum is only going to provide radiation dose to the patient and no useful image quality reasoning. We also have, when we measure the patient doses, we have a specialized thing called a dose calibrator. So this measures our activity. So we do what's known as quality assurance tests every day. And this is just making sure that we're measuring what we think we're measuring. And because we're working with unsealed sources, there will be spills, there will be contamination. So we do monitoring to make sure this isn't going to be spread throughout the hospital. And of course, we have to give it a deep clean once a week because we want to keep it aseptic as well. We do daily little cleans, but a deep clean once a week. We also have a pet department, and St. James's in Ireland was the first place in Ireland to do the gallium synthesis. So we have a very similar thing to the molybdenum generator. Thanks to some clever research scientists, we now have gallium available on site, and we prepare this twice a week on a Tuesday and Wednesday. And then we have to perform cleaning runs to make sure we're getting the gallium, like just pure gallium and no germanium. So it's similar to the molybdenum and technetium generator. And then with the radionuclide therapies, our patients are admitted on a Wednesday, so that's when they're administered the capsule. And then we do measurements on a Thursday and Friday, and that's just to see what the dose rate is, because once they get below a certain threshold, they can go back home and follow radiation protection restrictions. So that's another duty. So we have to explain, like to minimize the risks to others. So it's always a great challenge. We always get great questions. Everyone interprets it slightly differently. People's knowledge of physics is very different as well. So we always get fantastic questions during that, and we just want to make sure that we're just minimizing risks to the general public. And bear in mind that these therapies have been going since the 1970s as well. So if it wasn't safe, we wouldn't be allowed to do it. So I always try and tell my patients, this is quite an old area of medicine in comparison to some of the other modalities. We also look after our gamma camera. So every day we do tests on that as well. And we just want to make sure that we're seeing the correct disease and that we're not just seeing dead pixels and obscuring stuff. So it's really important that we're getting the proper diagnosis for the patients. And as I've been talking about the pharmacy and capsules, we generate a lot of radioactive waste. So this needs managing in a correct manner. We have licenses to follow. We're only allowed certain amounts of radiation and certain quantities for each radionuclide. I can't just decide one day to bring a new one in without contacting the Environmental Protection Agency. I have to get a license and be approved to bring it in. And we have to be mindful of what we're discharging to the sewers, and being able to store the radioactive waste until it's decayed and then before releasing it to the general waste facilities. I've talked a bit about contamination monitoring, and then we have other like analysis to do. So sometimes it's the radiographers doing the analysis for the patient, sometimes it's ourselves, it depends on the procedure, and the radiopharmacy orders as well. So we are buying the radionuclides, so there's a chain to follow, and we have to make sure we're ordering the correct quantities. A doctor might ask for a certain activity, so we need to make sure that we follow through, and as physicists we're the ones who are designated to buy these quantities of radiation, and there's all the transport legislation that comes with it, so there's a lot of chain of responsibility. So this might be a typical week, but I might also work on risk assessments and do calibrations. It's so varied. It's a very, very varied job. So hopefully I've done nuclear medicine some justice. I only had a short period of time to talk about it, but hopefully you take away from this that it's a really interesting area of medicine, and that nuclear medicine is the application of radioactive pharmaceuticals used to diagnose and treat patients. It's a great way of using your physics knowledge to help people. Nuclear medicine provides functional information, so we can see lots of wonderful things. We can naturally inject a patient and see the kidneys functioning. We can see just one kidney function better than the other if there's going to be a transplant. We can differentiate Parkinson's disease with iodine 123. There's so many wonderful areas, and we can also use it in other areas of the hospital, in surgeries, and a big area is radionuclide therapy that uses the like alpha, beta, and gamma emitters to treat people, not just in cancer, but for other diseases as well. And as Thomas talked about before, we've got theragnostics that's really having a breakthrough, and we're seeing more and more within the hospitals as well. So it's definitely a growing area still. So that's the end of my talk. So any questions?
Thank you, Laura. That's amazing to hear what you do, and so much of that we never see it all behind the scenes at the hospital. So really fascinating. I wondered if you can tell us how do you protect yourself? Because obviously you must be exposed to more radiation through your job.
And that's a very good question. So, one of the principles that we use in radiation protection is time, distance, and shielding in that order. So, we try and minimize the amount of time that we spend with radioactive material. So, just try and work quickly, get, like, a big part of that is the training. And then distance is a great tool. So, you double your distance, you reduce your dose. And shielding is kind of like the last resort, but you might need that if you're dispensing unsealed sources. We just want to protect ourselves with the syringe, and that reduces the dose greatly. And a fourth part that we don't always talk about is just using your brain. It's just like thinking about what you're doing, being trained, just taking a moment, not diving into stuff. So the more you learn, the more you can learn to protect yourself at the same time. And we have dosimeters on as well. So we monitor our radiation dose. It's not a live action thing, it's sent to an approved dosimetry service. Then we get the results. And so we can monitor to see, like, does someone have a higher dose than someone else? Is there anything, are they doing too many duties? Do we need to reduce what the activities they're doing? So there's always these questions as well. Because it is kept an eye on. But my dose last year for my whole body was 1 millisieverts. And background radiation in Ireland is 2.7 millisieverts. Background radiation in Cornwall is 6.7 millisieverts. So I would have received a higher radiation dose living in Cornwall.
That's interesting. So there's quite a few people here asking about how it feels for the patient to have a radiopharmaceutical treatment, both during the treatment and then afterwards. Do they feel more tired or sick, or what kind of things happen when you have one of these treatments?
That's a really interesting question. It's, the patients mostly are injected with the radiopharmaceutical and they don't feel anything. So it's just traveling through the body. It's not really interacting with many processes. Um, like this is why we say we want something chemically stable. Um, so a lot of patients don't feel anything at all. Maybe in the therapies, they might feel a little bit something depending on what type of therapy they're having. For the thyroid cancer, a lot of the time we hear like the patient doesn't feel anything. It's like having a headache tablet, and they might have a slight sore throat for the first 24 hours, but a lot of them don't report any symptoms.
That's great. I'd like to bring Thomas back in now, because I think something that all the audience members are interested in is finding out how you got into your respective careers, what the sort of pathway was, and maybe what drew you towards that. So maybe if we start with Thomas, tell us how you got into your job.
Well, mine is actually a story of serendipity. I came into nuclear physics because as an American scientist, I could go to a summer job in a US lab without a visa. And that my university found that so practical, they sent me into the nuclear path. After that, I was doing fundamental research at CERN when my former PhD promoter contacted me and told me, oh, Thomas, it's with a heavy heart that we have to announce that we're shutting down the lab where you did your PhD, and we don't know what we'll do with that dipole magnet from the separator. And that same afternoon, a colleague of mine at CERN presented the idea of MEDICIS, saying, the only thing I'm missing for the go-ahead is a magnetic dipole for the separator. So I sort of put one and one together, and that's how MEDICIS started. And of course, I jumped on that right away and embraced it fully. And that's how I became involved in radioisotope production. So serendipity, but also passion, excitement for the physics research that I was doing, I think is a very important part.
It's great to hear. And Laura, how about you?
So I started as an undergraduate at the University of York, did a master's project related to nuclear astrophysics, fell in love with that area, started doing my PhD, started doing outreach with binding blocks and trying to find out a little bit more about nuclear medicine so we could talk about, like a positive benefit of nuclear physics. And there's many. And then unfortunately, a member of my family got diagnosed with cancer. They were undergoing radiotherapy. So I started doing more research to be able to speak to my family about what was going on. They had lots of questions. And I found it a really interesting area and applied for a training scheme and got on. So it was kind of like a small evolution, starting off like the nuclear processes in stars to the nuclear processes in people.
Yeah, it's great to hear. Somebody here is asking, Thomas, what's it like to work at CERN? People are interested in this. What's it like there?
Well, it's actually fantastic. I call it Disneyland for scientists. It's such an invigorating environment. It's highly cosmopolitan. You've got people from all around the world joining together to try to answer those fundamental questions of science, but also provide for society, as with the MEDICIS facility. It's also a very demanding environment. You feel so pushed to deliver, to really do your best because you are with the best. It's, well, going 120 miles an hour and not stopping. And so I must say that after 3 years of doing that full time, I was very much drained and very happy when I moved to Manchester. But now that I go back there just on timely basis, I really love going there and doing that. One thing people might realize at CERN as well is the buildings look a bit shabby from the 70s and not being well tended. But it's because all the money we get, we put into the machines. It's really state of the art, at the forefront, if not beyond the state of the art, so that we can realize all the great science that happens there. So very much enticing. And if you get the opportunity to go, I recommend it to everybody.
It sounds like a must have. It sounds great. There's lots of questions coming in for you, Laura, about people asking, has there ever been a misdiagnosis, and do patients, have they ever received unnecessary doses of radiation? So I guess you have procedures in place to stop this happening, but tell us a bit about that.
Yeah, and this is a big part of why we have legislation as well, because if you think back to the early days when they first discovered X-rays, they got very excited and started just irradiating people and not knowing about the harmful effects. And so over the years, like the more information that we get, like we refine it, we have optimization techniques as well. So part of a job as a physicist is trying to get the right radiation dose and the right image quality and make sure that the patient also gets diagnosed. So there's all these different components. Unfortunately, patients are misdiagnosed. This is why the strict like legislation to try and minimize that. And sometimes there's human error, sometimes the machine error. So, patients might be at the unfortunate end of receiving a higher radiation dose than expected, but these have to be reported and investigated as well to make sure it doesn't happen again. It's not something that's taken lightly. So, like a physicist will also do a dose incident report as well. So we get informed if a patient, for example, they've picked up the wrong patient. There's two patients with a similar name, and someone's come forward, and like this is why we have ID checks. There's many scopes for things just falling through the cracks, and then the physicist will like look into like what happened. Was it a wrong patient? That's definitely reportable. was it the right patient, but the wrong limb, like x-rayed and do a dose calculation, what was the risk, like how much of that's reported to, like does it need to be reported as well? So, it's hospitals are full of humans,
Mm-hmm.
but we do follow strict legislation to try and minimize any harmful effects.
It sounds like, yeah, you have to be somebody who's good at doing those calculations and taking it seriously.
Yeah, and we're always trying to refine the way, like the best way to dose, like to calculate dose to patients.
Um, Somebody here, this is a question for Thomas, really, maybe. What do you think the future is of nuclear medicine? I wonder if you can tell us a little bit about how long it takes to develop a new medicine, and what do you think is exciting then on the horizon?
Well, yes, as I said, the research I'm doing is just beginning because between me finding that really cool isotopes and Laura injecting it to a patient, we need to have all the different stages of research. First, into refining its production and reaching a quality for the product that's sufficient for medical application. You have to make sure it doesn't have any impurities. You have to make sure that you also understand all the radiation. Many of those isotopes were studied back in the 70s with poor technology. And so it is insufficient knowledge at the moment. So we have to redo those measurements much more carefully. Beyond that, we have to start to see how we can engineer the necessary molecules that can turn them into a radiopharmaceutical. Once we have one that we think might be promising, we have to see, is that a stable enough molecule? Is that going to hold that radioactivity? Because you don't want to have loose radioactivity in the body. And is it going to be specific enough? Is it going to target the cells that you want to target and not other cells? So you start to make tests in test tubes or in petri dishes. Once you're satisfied with that, you start testing it in small animals, in mice, and seeing how it behaves, how it goes. And once you've gone through that extensive process that takes itself 5 to 10 years, then you can bring all that knowledge together and turn to the different agencies, the regulatory bodies, the NHS, the government, and tell them, look, I believe this can be used in patients. And then they will study it and give it back to you and say, okay, show me. Then you have to select first patients who are so far down the line, they have no other options. And then you can try it in one and maybe in 10. And if you see, oh, actually, we're having a positive response there, they can give you a go ahead to go to more. And then you try to 100. And then you try to compare the new therapy you're proposing to the standard of care. And are you providing better care? Because if you're providing just the same, it's not enough. But then once you start to establish that, oh, maybe it's something good, you don't want to do the mistakes of the past, saying, we're going to give that to everybody like they did with the radiation. Can you believe 100 years ago, people will spread radium on their face because it was giving them a perfect face until their mouth starting falling off? Because it takes years. It takes buildup of radioactivity in your body until you start seeing the symptoms. So you also have to follow those patients for 5, maybe 15 years before you can say, yes, this is the new standard of care. So between the preliminary study and the follow-up studies, you are easily 20 years into the research.
And is there anything on the horizon that's or nearly at that 20 years of having had the research?
Let's say that from the new isotopes we are developing in our lab, we've identified one for which we are ready to tell the regulatory bodies, let's try that in humans. It's the samarium 153 isotope, and we are hoping that within the next 2 years, we will go to first in human trials, knowing that we started those investigations only 2 years ago. So we really fast-tracked that research as fast as we could.
Wow, that's exciting. Oh, great. Um, right, so some more questions. We've not got much time left. Let's squeeze in a few more. Somebody here is asking, why aren't all cancers currently treated using radiopharmaceuticals? And do you think that's something that we'll move towards in the future? That's probably one for Laura.
I think sometimes when we say cancer, we think of like one disease, but it's actually an umbrella term for many different types of diseases. So it depends on the research that's gone into it. Some cancers will be better for radiotherapy, some will be better for surgery, some will be better for radionuclide therapy, some with chemo. There's so many advances. So unfortunately, there's not a magic bullet and there's no like one size fits all. So it really depends on like what's being developed by researchers and what's available. So we see stuff like radium 223 that's been fantastic for bone metastases for prostate patients. We're seeing PSMA, like lutetium PSMA for patients with prostate cancer. Like there are advances, but unfortunately, it's not so simple as just one treatment for a big amount of diseases.
And just thinking, somebody here is asking, Thomas, do you ever work directly with patients? Because you mentioned that you go all the way through up to this trial stage. Do you hand it over to somebody else when it gets to the stage of working with people?
Yes, indeed. It's actually a very large effort by many members of a collaboration. I am the little cog at the start that produces the radioisotopes, but I never work with patients. However, I make a point of talking with as many medical doctors as possible so that I can promote the sort of future that we want to create and make sure that I can work with them. But it's more people like Laura who will be close to the patients.
And a nice question here from somebody in hospital. What's done to reduce the isolation that the patients might feel while they're having their treatments?
I think that's a really nice question because, we are very mindful of the fact that our patient might be in by themselves for at least 2 days, could be 5 days. So we, try and make the suite as comfortable as possible. We have a TV in there. Today we have a smart TV with Netflix available. The patient can bring books and board games. So we've got a large selection of books because they have to be left in once the patient leaves. We've got a computer in there so that, like they can still browse the internet. Um, we try and make it as comfortable as possible. And I know the patients are very glad to get home by the end of the couple of days, but some people think it's a kind of like a way of having some peace and quiet for a few days.
Mm.
It really depends on the patient, but yeah, it is very isolating and heartbreaking for them.
Yeah, for sure. I think sadly we've run out of time, and there's still more questions coming in. So that's that's a shame. It's been really fascinating. I'd suggest the people who haven't had their questions answered, maybe if you submit them to the website, and we might be able to pick up some of those questions later. But for now, all that remains is to say thank you so much to Thomas and Laura. It's been a really fascinating evening and so many new things that we've learnt, and just wonderful to hear what goes on behind the scenes. And thank you to all of the audience. Just to let you know that the recording of this event will be available on the Nuclear Masterclass website later this week, probably. Thank you all for joining us. And of course, this is the last one, so I hope you've enjoyed them. And now it just remains for me to say have a lovely summer. Thank you. Good night.